Let's have a look at the Kalman filter theory. I recommend you to read this tutorial on kalmanfilter.net. It provides several examples and it's very well written. I tried to explain it in my thesis, but it's in Spanish, so I will explain it in English. Okay, so a Kalman filter is basically an algorithm that estimates the most probable value of your variable system. So in this image you can understand how it works. So the exact position where the car is calculated with the Kalman filter, and so it do like an average from the predicted state and the measurement itself. This because in the real world the sensor and the predicted state are not exact, so they have a probability connected to that value that is represented with this curve, with this Gaussian curve. So for example, in a measurement, when the sensor give you a data, it's for sure below this curve, and this curve is tighter if the accuracy of your sensor is very good, or is wider if it's not so good. So the Kalman filter estimate the most probable value between the measurement and the predicted state. So it's divided into steps: the prediction and then the correction, and those are the formula, the equation of the Kalman filter. So the prediction is based on the model of the system. So I can predict the next step, like I can predict the variable of the system at the time k more 1 if I know the state at instant k and the input at instant k. More Gaussian noise. So in my case, I defined the variable of the system, the x and y and theta position, the x and y position, and the theta orientation is the orientation of the robot, and the speed in x, y, and omega, so the rotational speed. And the input are the speed of the wheels of the robot calculated with the encoder. So this equation that calculate the predicted value of the variable of the system is calculated with F matrix, that is the evolutional matrix, and B matrix is the control matrix. So the matrix F contains the information of autometry. So for example, this is matricial operation, so F is multiplied for X. So the X position is X more delta T is the time step of the cycle. So if I executed the Kalman filter each 20 milliseconds, that is the Arduino loop as well, delta T is 20 milliseconds. So X is X more the time for the velocity nx, as well as E and as well as theta, and there are this equation written better, like the next position next is the actual position next, more the speed for the time. And the B metric is the control metrics, and it's basically the cinematic of the robot, and I calculate the speed of the robot. Okay, so as I told before, the model and the measurement as well have probability connected to the value. So this is called covariance. So in the Q matrix there are stored the covariance value for each variable of the system. So if you give a low value at the covariance, it means that your data is very good, so this is very tight, this curve is very tight, so the Kalman filter tend to trust more that data. For me, in my case, the calculated odometry and the position is very good, so I gave it a small variance and a bigger variance to the orientation. Those are all experimental value. I defined my measurement, that there are data from the IMU, the X and Y position from the LiDAR, and the orientation from the LiDAR as well. So you have to define H matrix to perform correctly the Kalman filter, and this one. So it basically say that the orientation of the IMU and the orientation of the LiDAR correct the orientation is in the third position, so multiplied for X for the state goes to correct the orientation of my robot, and the X from the LiDAR, it's in the first position, so here is multiplied for X as said before, and goes to correct the X position. I assign the variance of this variable provided from the LiDAR and from the IMU as following the matrix R. So I assigned a very good variance to the position from the LiDAR and a bigger variance to the orientation, so R11 and R44. Here it's the explanation of, it's better explanation of the curve. So when you have a measurement, it can be in this area, and this is the probability. So better sensors, so with higher accuracy, have a tighter curve here. Okay, so when I implemented the first time the Kalman filter, that was the result of the experiment. So the trajectory was a square, but as you can notice, when the vehicle tried to go to the position, it go slightly away, so it go after the position, it passed the position, and then go back to the trajectory, but at each point, and was the target point, it passed that position. That I discovered because the LiDAR position, okay, it's very good, but it has a delay. So in green I have the GPS data, so the real position, and in blue the LiDAR position. As you can notice, when they are at the same position, there is almost 1 second of delay. I didn't know if that delay is 1 second exactly, because these data are plotted with MATLAB, so also in the transmission I have a delay, and I don't know exactly this delay, but for sure there is a delay between I get the LiDAR data and it processes through a SLAM algorithm to get the position. Okay, I will try to explain the LiDAR problem with this image. So as you can see, the vehicle at the starting position P0 and time 0 travel at the position P1 at time T1. So when I received a position from the LiDAR at this time, it's the position measured at time T0. So there is this delay and this position. So I try to correct the measurement of the LiDAR using the position of the LiDAR, more the average speed for the delay. So the implementation of the Kalman filter in Arduino is divided in 2 steps: the prediction based on the model with autometry and kinematic, and then the correction, the update, just when the LiDAR data are available. So the input vector are the velocity, the speed of the wheels, and this is the LiDAR delay in milliseconds. So if LiDAR data is available, I correct the Kalman filter, execute the correction step. So the observation vector that is in the theory set vector is the IMU orientation, and the LiDAR position in X, more the correction, and the LiDAR position in Y, more the correction, and also the orientation from the LiDAR with the correction. So I perform the update of the LiDAR, and if the data is not available, I just predict. I just executed the prediction step of the Kalman filter. So I'm using the model of the system to predict and estimate the best state.